So we are streaming, everything is on. So it's good to check with me, every morning, every class, just to make sure that the recording is on, the audio is being captured, and we are streaming. Because this way, you don't have to be busy copying everything on the projector or whatever I say onto your notes. You can focus on your own understanding of the topic and write that down on your notes. Okay? I know I have said it before. All right. So what we'll do today is to continue our discussion on Tuesday. And we have already talked about, like basic idea of base conversion. We did an example, remember? We have one, two, four, $8 bills, and then the coins are, half dollar, quarter dollar, eighth dollar, and so on. So I'm hoping that particular analogy of using how to make change, convinced, all of you that you already know the basic idea of base conversion. It's just that, well, can we formalize this? Can we make it, more mathematical? So that's kind of the focus of today's class, is to make that more formalized. If I give you a value and I ask you to express it in a particular base, do you know how to do it? If I present a number in a particular base, can you figure out what value it is representing? So that's going to be the focus of today's lecture. And we'll start to look at numbers in a more kind of formal or mathematical way. So what I'll do is I'll start with this little bit of mathematical notation here. Now, by the way, this is all in the notes, and the notes have been available to you since day one of this entire semester. And I have recommended all of you to read ahead of me. So I'm hoping that this is not new to you, because this is the module that we are on, and I would like you guys to kind of at least read the module that we are on a little bit ahead of me. Okay, so we'll look at this particular equation here. V is just the value. Okay, so V is representing the value that we are concerned about. The number is representing that value. Okay, so the number has digits, right? All the numbers that we know have digits. So D0, D1, D negative 1, D2, D3, those are all digits. D0 is the digit that is representing how many ones we have. And then D1 is the one representing, in this case, because we're dealing with base 10. So D1 is the digit that tells us how many tens we have. D2 would be the digit to tell us how many hundreds we have, and so on. Now, on the other side of the decimal point, we can have D minus 1, D subscript minus 1, which is representing the quantities of 0.1, or 1/10 in the case of a base 10 number. D to the with a subscript of -2 will tell us how many hundredths do we have in the value that we want to represent. So is that okay? Does everybody understand the D, what the D's are representing? We're good with that? Yes? Okay. And in this specific case, we're dealing with a base 10 number. So the base, well, I just said it's a base 10 number. So what do you think is the base? 10, exactly. So that's why we are seeing powers of 10 instead of powers of something else. 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and -1, 2, and so on. Okay? We can assume a number has an infinite number of digits. Okay? And you say, well, but what about 3? Well, 3 technically has an infinite number of digits. It's just that we do not write out the non-essential digits. Because if you think about the number 3, okay, in base 10, for instance, you can kind of imagine there's an infinite number of zeros to the left-hand side of the 3. Well, they are not particularly useful, because all that is telling us is we don't have a 10, we don't have 100, we don't have 1,000, we don't have a 10,000, and so on. So they are not really changing the value being represented. So instead of writing all of those zeros, we just go like, well, let's not write those zeros, because they are not adding anything to what we need to know. Same thing to go for all the places to the right hand side of the decimal point. 3.0 is the same thing as 3, because that's 3, but we don't have a tenth. there, and so on. So you can say that implicitly we have all of those zeros. It's just that because we don't need those zeros, we don't write it out. Is that okay? So this notation, sigma notation, is what we call a summation, notation. You can look at it as a loop. Okay. What you do is you look at it as a loop. I is the variable that is being changed per iteration. The number associated with I at the bottom of the sigma notation, sometimes it's below the sigma itself, is telling us where we start. For each iteration of the loop, you increment I by 1. And then the upper number here, which in this case is infinity, but sometimes it's not. It is telling us what is the upper bound. When do we get out of the loop? The expression we need to evaluate per iteration is this part here. Okay, so per iteration we evaluate this portion here and figure out the value for that particular value of I. Is that okay? And then what we do is we add that value to a random sum until the entire loop is done. Questions about the sigma notation? It's a summation notation. Okay, let me give you another presentation because I think some people get it and some people may not be 100% getting it. So let me use Zerno. Let me get back to the one that I want to use, which is this one. And I'll give you a general notation of sigma, and then I'll give you the equivalent code in quote-unquote pseudo C code. Okay. So I'll open a new page, and we'll just focus on this one single expression. I goes from A to B, and this is some function depending on I. This is kind of as general as I can make it. Basically, A is the starting point, B is where we stop, and the value per iteration is just f of I. It's a function of I. It can be very simple, can be even a constant, okay? Can be something very complex. I don't even need to know because I just want to show you what this notation is representing. So are we good? Okay. So now on the side, I'm going to keep this one in view, but then on the side, I would use my editor to show you the equivalent C code of this notation. So let's go ahead and do this. I'm going to get rid of that. Okay. So we'll look at it as a function. And for the time being, let's just say that f of I returns an integer. Okay. But that's an assumption. Okay. It doesn't have to be an. What about this? Just say it's a value. Okay. And this is sigma. And we have a few variables. We have A as a value. We have B as a value. And then we have the function f. Okay. Have you guys ever learned how to pass a pointer to a function in cisp310? Yes? No? Does it sound vaguely familiar? Okay, so I'm going to use that notation. If you don't quite get that notation, it's okay. It's not a big deal. Of course, I have to remember that notation too. I think it is this. Oh. There we go. So as I said, this is not actual C because C has no type called value, right? So value is can be float, can be double, can be int, can be unsigned, can be anything that is appropriate. But the point is, when we deal with sigma, there are three things you need to tell it. Where do we start? Where do we end? And then for each iteration, what is the value that is based on the index of the loop? Okay, so those are the three pieces of information that we need. So now, what is it doing? Well, it's doing something like this. So we start with a sum as a local variable, which is initialized to 0. And then we just have a loop. The loop has I as a value too. So there are several ways to do this. I'm going to use just regular C instead of C++. So I would say I starts with a value of A as long as I is less than or equal to B, because when I equals to B, that is still one last iteration that I need to consider. Is that okay? So it's not less than, but it has to be less than or equal to B. And then for each iteration, I'm just adding 1 to I. Inside the loop, all I'm doing is I am saying sum plus equal to f of I. There are two ways to use f as a function as a pointer to a function. This will actually work. Okay, and then after everything is done, I return sum. That becomes the value of the expression. Is that okay? Does everybody understand now what the sigma notation is about? All it's doing is going through a whole bunch of iterations. For each iteration, there's a value, and we're adding up all those values to a sum. And the sum becomes the value of the expression, of the overall sigma expression. So are we good with this? All right?
Sorry, it's about the notation of the parameter list in the function. Are we pointing to the address of a function in the third argument?
Yes. So for this particular argument, or in this case, it's called a parameter, because when you're looking at the definition of a function, it is called a parameter. So f as a parameter is a pointer to a function that is expecting a parameter that is of the type value, but it is also supposed to return a value as well.
Okay.
Yep. So yeah, it's a pointer to a function, which is a slightly more advanced topic. I'm not really sure whether they covered that in cisp310, but it's a very useful concept too.
Right.
So are we good so far with the sigma notation? Okay, for those of you who have taken pre-calc or calculus, you would know what a sigma is, because an integration is basically a sigma where the incremental steps is infinitely small. So, well, I shouldn't say infinitely small, it approaches 0. Are we good so far? Yes? Okay. So if we're good with this, we go back to this expression. So do we have any questions about this expression? It really is just a mathematical way to express something that you have known since elementary school. Ever since you know what a double-digit number is, you have been using this already. So is that okay? All right? Okay. So what if we're not dealing with a base 10 number? What do you change about this when you're dealing with a base B number? You change the 10 to the B, right? That's it. So whether you're dealing with base 2, base 10, base 16, those are all common bases in computer science and math, or some really odd base like base 7, it doesn't matter, because all you're doing is changing the base. Instead of base 10, changing to whatever base you're dealing with. Are we good so far? Yes? Okay. So that brings us to the next expression, which is more generalized, because this one is basically just saying, well, you can parameterize the base itself. So in this case, the base is just B, okay? B can be 2 for binary, it can be 10 for base 10, it can be 16 for hexadecimal, it can be 8 for octal, so on. D subscript I is still indicating which digit we're talking about. Is that okay? Do we have any questions about this portion here before we move on to section 5? No questions? All right. So now we're moving on to section 5, which is converting a value. You are given a value V, and I want you to present that value as a number in a particular base B. So how do we do this? Well, let's do it by hand first, because if we know how to do something by hand, maybe that will give us an idea of how to do it mathematically or use an algorithm to do it. So I'm going to use an example here. 481, okay? That's the base 10 representation of the value that we're concerned about. And we want to convert it to a base 7 number, okay? So in reality, there's no particular reason to use base 7, okay? Base 10 is already a stretch. The reason why we use base 10 is because my gesture is actually giving you the answer. Because we got 10 fingers, okay? And that's just coincidental. If we had 8 fingers, that actually would be better because base 8 is much better than base 10 from many perspectives, okay? It would be also be nice if we had 16 fingers because base 16 or hexadecimal is also a very nice base to use. It would also be nice if we only had 2 fingers or hoofs, okay? Because that would be base 2. Base 2 is also a very nice base. Base 10 is just not a very nice base. I'll explain why that is the case, okay? But we'll choose an even more strange base, which is base 7. I call this the drunk octopus base. Because an octopus has how many arms or, tentacles? It's got 8, right, octo. But it is using one to hold on to a can of beer. So it only has 7 for counting. So that's why I call 7 the drunk octopus base. Which is the only thing you guys will remember when you walk out of this classroom, right? You will forget everything about base conversion, and in your head there's an image of an octopus drunk with one can of beer on one tentacle. And how do you drink beer underwater? So that would be the question. That's your homework assignment. All right, so how do we convert it? Well, so let's just say that we have D2, okay, D2, D1, and D0, okay? I know for sure 3 digits, well, maybe not enough. Let's make it a D3 as well, okay? So the end result would be 4 digits, okay? I'm going to allow myself 4 digits to represent the value, which is known as 481 in decimal, but I want to express it as a base 7 number, okay? What is the job of D0 in this case? It tells us how many 7 to the power of zeros do we have, right? Well, that's just a fancy way of saying 1. How many 1s do we have? How many 7s do we have? How many 49s do we have? And how many 343s do we have? Very good. So which end should I start first? Remember the change that we worked out in the previous class? Which end should we start with? Okay, we see a whole bunch of hands pointing to the left, and that's correct. So let's start with that end. And I would even write down the values each digit is representing. So this is 347? No, 3. Okay. My arithmetic is awful. This one is 49. This one is 7. And this one is 1. Okay? So we look at the value that we want to represent, which is 481. We say, yeah, we'll need 1. 343. So now we do the math. 481 minus 343, because that would give us what is left. So that would give us 138. Is that right? Okay. So we look at 138 and say, well, the next power of 7 is 49. So we ask how many 49s can we fit into 138? The answer is 2, right? The answer is 2. So now we know there are 2 of these. So now we take 138 and subtract from it 2 of 49, which is 98. So that would give us 40, if my math is right, right? So we look at 40 and we ask, well, how many 7s can we contain in 40? The answer is just 5 of them, okay? So we got 5 of those, and then we subtract 5 times 7, which is 35 from 40, and that would give us 5. And now we have 5 left. So here we have it. Okay, the base 7 representation of what we know as 481 is 1255 in base 7. So are we good so far? Okay. So this is generally speaking, how we do base conversion. Just in terms of the principle or what we need to go through mentally. This is how we do conversion. Is that okay? So the next question is, what if I'm interested in just singling out one particular digit? Okay, I don't care about the other digits. I just want to know one. Okay, so is there a equation to do that? So let's take a look at another example then. So we'll take a look at another example and we'll figure out, this is the number that we're concerned about. And we know that, it has D3, D2, D1, and then also D0. But this time, I'm only specifically interested in D2. I don't really care about D0. I don't really care about D1, nor do I care about D3. How do I single out D2 and figure out what D2 is supposed to be? So, we can keep base 7. Yeah. So in base 7, how do we just single out that D2? What do you think? So the first thing we do is, well, how do we get rid of the lower digits? What is the mechanism to get rid of the lower digits? So let's go. Let me repeat what we had, which is this digit is representing the number of 343s. This digit is representing the number of 49s, number of 7s, and number of 1s. So how do we single out the number of 49s? Well, here's a question. With D0 times 1 plus D1 times 7, can that sum be more than 49? Or at least 49? Let's say we put a 6 here, which is the largest value you can use in base 7, right? So we have 6 times 1. And we put a 6 here too. And then we have a 6 times 7, which is 42, right? 42 plus 6 is 48. And it is still less than 40. Well, the first thing we need to do is to do a division. We divide the number by 49. 49 is the quantity that the digit that we are concerned about. It's what it is representing. Okay. Okay. So we do a division. So the first thing we do is we take 861 and divide it by 49 because 49 is the power of 7 that D2 is a factor of or multiplier of. Okay. So we divide that. And just so that we know that we are only concerned about the quotient of the division and not so much the remainder or the fractional part of the division, let's just take a 4, okay? Just so that we focus on only the integer part. Does everybody know what a floor is? Okay, a floor function. So let me define that because we'll need to use that in this class later on anyway. So the floor of x is basically the largest integer that is less than or equal to x. That's how it is defined. Let me run a few examples through and to make sure that we understand what a floor is. So what is the floor of 2.3? What is the largest integer that is less than or equal to 2.3? Just 2. Very good. And what about the floor of 2.8? It's still 2. Very good. What about the floor of 2? 2. What about the floor of negative 2.3? 0. No. Not negative 2. It's negative 3 because it has to be less than or equal to. So it's a trick question, yes. It is not the same thing as, it's definitely not rounding, because for rounding, rounding 2.8 will give us 3. But it's not truncating either, because if it's truncating, then truncating to negative 3 would have given us negative 2. So floor is kind of like a little strange thing, because it's always going for the smaller or equal to integer compared to the number that we are concerned about. But I think we kind of know what it is, right? Okay. All right. So once we have done this, what do we do? Because once we have done this, we will still have to deal with the quantities that was originally the number of 343s. Yes?
Well, you'll get number 49 in the equation, or the D2 number, and you can divide that by 7 to figure out how many.
Not dividing it by 7. You're very close.
Divide by 6.
No, not dividing. It does use the concept of dividing, but you're not focusing on the quotient. Because if you divide this number by 7, you end up with getting rid of D2 as well, and then you're moving on to D3. So you're not doing division, but you're trying to specify an operation that relates to division, but you're not focusing on the quotient. Mod, exactly. So you take this number, and if you mod it with 7, then you get the digit back. Okay? So let me just go here, and we say mod, which is a percent symbol in C and C++, 7, and that will give us out the answer. Is that okay? That will give us D2, to be more specific in this case. Yes? Okay, so that's one of the operators that cisp310 really should have covered. Mod is the remainder of a division. So you can look at, so A mod B is the remainder of A divided by B. Okay? So, all right. So do you think I should just kind of stop here, because I just kind of gave you the general sense of, what I think, should work, with a heavy emphasis on should? You don't take it. You really should not take it, as since TAC, said it's probably working. So we need a proof, right? Some kind of, at least if it is not a proof, a verification. There's a main difference between the two. A verification means, at least in one instance, it seems to work. Okay. A proof means, we have definitive logic derived truth that it works in all cases. So those two are entirely different things, but we would like to have at least one verification. Yes? Why is it mod 7? Because if I do not mod 7, then the other digits to the left hand side would interfere. So I would end up with a number, this expression without the mod 7 can potentially be a number that is greater than 6, which is not appropriate, because we are looking for a single digit as a base 7 number, so it can only range from 0 to 6. I have to get rid of the extra stuff. Okay, so let's check it. Now, I'm very lazy and I'm very bad at arithmetics. So how do I check something like that? Use a calculator, right? But I don't like a calculator either, because if I use a calculator, you cannot see it. Now, yes, I can use a calculator that you can see, but there's a better way to do it. It's called a spreadsheet. You will see throughout this class that I use spreadsheets for a lot of things that most people would not imagine using a spreadsheet for. Okay? Especially after the second half of the class, you will see. So let me just work out the spreadsheet in this case. And instead of using a regular spreadsheet like LibreOffice or Microsoft Office, I am going to apps.losrios.edu. So this way, I can share with you, the spreadsheet that I have done in today's class. So we go to Google Drive, go to cisp310, and there's a folder here that is already shared with you. So everything in here is already shared, and I just go to examples and make a new one. So new Google Spreadsheet. And it warns me that this is also visible to all of you because it is already in a folder that is shared, and that's the intention, yes. So we say, yes, let's go ahead and do it. Okay, so we'll start with value to convert, and we'll use exactly the same example that we have here, which is 861. Okay, 861. And I'll even make the base parameterized so that later on, if you guys say, I want to know what it looks like in base 6, well, you can do it, right? And which digit? So I'm using the same notation as the subscript of D. So in this case, it is 2, but you can change it to other ones if you want to. And then the digit value is going to be an expression. Let me zoom in a little bit so that you can see actually how I enter the equation. Okay, so it is the floor of this number divided by 7, which is our base, raised to the power of this value. Okay, I'm parameterizing everything, so this way I can reuse it later on. But also, I also need to use a mod on the result of the floor. So I need to put a mod function on top of everything. And it's going to be modded with the base, which is this number here. And that becomes the whole expression. I know this is not an infix notations because the mod is on the outside, but do we understand how this formula in a spreadsheet is really doing the same thing as the expression that we looked at in Notepad, Mousepad? It's mod, okay? Instead of an operator, it becomes a function that takes the value that this is called the dividend, this is the divisor, but it still gives us the remainder of the division. Are we good? So let's check it. It says it's 3. Okay? It's very good. But is that actually the answer? How do we verify that this, in fact, is the answer? That becomes the next question, right? Okay, so let's check it. So instead of just checking one single digit, let's check all the digits. So it says right here that the digit 3, D3, is supposed to be a 2. Okay, and we just looked at digit 2 earlier, but let's do it again. It's supposed to be 3. Digit 1, excuse me, it's supposed to be 4. And digit 0 is supposed to be 0. Okay. So the base, the entire base 7 number representing what we know as 861 is 2340 in base 7. Okay? Well, but it doesn't tell you whether it's right or not. Because as long as it is generated by the same formula, it just spits out a bunch of digits. But there's no, by itself, you have to convert it back into base 10 and see whether we get 861 back. So how do we do that? Well, to do it quickly, we can do it this way, but let's do it in a more systematic way. Well, do I want to do it that way? I don't want to use a too complex way to do it, so we'll just go ahead and do it in kind of not too complex way. So we take this number and multiply by 1, right? Because that is representing how many 1s we have. We take this number, multiply by 7, because that's representing how many 7s we have, because it is a digit of a base 7 number. We take this number and multiply by 7 squared, which is 49. And then we take this value and multiply by 353, which is 7 to the power of 3. Okay, very good. Oh, 343, thank you. And we get 861 back. So this is a verification that the process works. Is that okay? So do we have any questions about all the material that I have talked about up to this point about base conversion? Because I have just illustrated how to convert a value, pick one digit and figure out what that digit is supposed to be. Once you figure out all the digits, this shows us how to convert that number in the particular base back to the value it is representing. So, are we good? Okay. Now, of course, we are not going to use base 7 too often in this class. I use it just because it is a very kind of strange base to use, but it doesn't matter. It really does not matter at all. If you want to use base 9, in this particular example, change this to 9. Okay, that will change, and then you just say which digit are we talking about. Let's say digit 1. It tells us that digit 1 has a value of 5. What about digit 2? Has a value of 1. What about digit 3? Also has a value of 1. So this spreadsheet just gives you the ability to do all that stuff. So are we okay so far? Okay. So now let's get back to the notes. I think it's here. That's right. Okay, so the equation that I just entered into the spreadsheet is really just the spreadsheet version of this. Okay? V, which is the value being converted, divided by B, the base, to the power of whatever digit you are interested in. This is the floor function symbol. Okay? Take the floor of that, and then use a mod operator so that you isolate just one single digit without the other higher powers interfering with the digit that we're interested in. And that's it. And this technique also works when I is less than 0. In other words, if you want to figure out what is the hundredth of something, or the two places to the right hand side of a decimal point, it works too. So it's kind of cool because it's kind of like a universal equation to figure out a single digit, whatever base you choose to use. Are we okay? All right. So the rest, which is not a whole lot from this module, just kind of focuses on base 2. Because we just took a big detour because the base that we are truly interested in is base 2. Because when we look at the inside of a modern digital computer, it is all binary. Okay, we are looking at a voltage and ask, is this voltage above a certain threshold? If so, we interpret it as a 1. Is the voltage below a certain threshold? If so, we interpret it as a 0. So we are only interested in 0 and 1. We are not really interested in anything in between, and that's why we have binary numbers. Okay, it's base 2. So in base 2, let's see. So in base 2, this is an example of a number in base 2, 01101 in base 2. So the question is, well, what value is it representing? Well, you just reapply what you have learned earlier, today and also on Tuesday. This 1 tells us how many 1s we have, which is 2 to the power of 0. This 0 tells us how many 2 we have, because it's 2 to the power of 1. 2 to the power of 2, we got one of those. 2 to the power of 3, we got one of those. 2 to the power of 4, we got none of those. So the value being represented is 8, what we know as 8 plus 4 plus 1, which is 13, in base 10. Nothing new at all. Okay, we are just reapplying what we have learned, but this time we just say that base is 2. How do we interpret the 0s and 1s? Are we doing okay so far? So all the ints, all the unsigned, all the signed, and so on and so forth in cisp310, underneath the variable, they're all 0s and 1s. Okay, so when you say int x and then you say x equals to 13 in this case, underneath we basically have memory, bits in the memory to represent these particular digits. Now you might have a whole bunch of zeros to the left hand side because you have a 64-bit integer. But the least significant four digits would be 1101, and everything else would be zeros. Are we doing okay at this point? Okay. So this part, section 7, just talks about, how a value is represented in the computer. It's basically in base 2, which is something that I said, already in this class. So I'm not going to repeat that particular paragraph. And this section 8 is asking you to, just as an exercise, write a program to do the conversion. So write a program in C or C++ or whatever programming language you feel comfortable with and do a base conversion. And for flexibility, you might even want the program to parameterize the base as an input. So input would be the value being converted in base 10, the base to which you want to convert to, and then it will print out the same value but in a different base. So try to write a program like that. You can also write another program where it inputs a particular number and then the base it is in, and it converts into the base 10 representation and print it out. So those things would be good exercises to do. I'm not going to grade it, okay? So you don't have to get it to work, but it is at least a good thought exercise to go through, just so that you get more chances of practicing, what we have introduced up to this point.
How are you doing this on an exam? Are we doing it as a code?
So in an exam, I would give you specific values and then tell you which digit I'm interested in, and it will ask you to show all your work. So you have to show me the derivation to show me how you can get to the value of a particular digit in a particular base. Or I can give you a number in a particular base, and then I'll ask you to derive the value in base 10. But you have to show me the steps as well. So it's not just one shot. You have to show me how you got to it. Okay? All very good questions. You guys got some questions? Got some additional questions at this point? No additional questions? Well, if there are no additional questions, we're going to move on to the next module, which is about adding and subtracting. Is this the two-state? Yep, this is the right one. And so today's lab is base conversion. It's going to be open by the time we get to the lab. So the next module is about binary number addition. All right. And just like the other module, it starts off talking about base 10, okay? How many people remember how you learned addition? I really cannot, but some of you may be able to do it. And do you remember the concept of carry? Now remember, we can do addition by counting pretty easily. What is 2 plus 3, right? Okay, 1, 2, that's 2. And then plus 3, 3, 4, 5. So 2 plus 3 is 5. Okay, that's pretty easy. What is 7 plus 5? We got 7, okay, 8, 9, 10. Uh-oh, I'm running out of fingers. So now you have to do a carry. Remember there's a carry somewhere else, and then you start counting from 0 again, and then you have the 1, 2. So it is basically 5 plus 7 is 2 with a carry of 1. And once you learn the concept of carry, then you can perform multi-digit addition. Because you cannot do multi-digit addition until you understand what is the concept of a carry. So are we okay? Are we comfortable with base 10 addition and also the concept of a carry? Yes? Okay. So let me ask you just quickly, and you tell me what goes through in your mind when you come up with the answer. What is 7 plus 9? 16, or 6 with a carry of 1. How do you know it? I do not see anyone counting fingers. I do not see anyone pulling out a calculator. So how do you know it? How did you come up with that answer so quickly? Because you got it memorized. Okay? But do you remember how difficult it was to memorize, which number plus which number is this number with a carry or without a carry? That took a while, didn't it? What about subtraction? Now, we'll move on to subtraction eventually, but let me just ask the question. What about subtraction? Subtraction is harder, isn't it? Because it is not commutative. Addition is commutative, which means 4 plus 3 and 3 plus 4 are exactly the same thing. So you don't have to memorize the entire matrix. You only have to remember one half of it, because the other half is a mirror image. But subtraction is not commutative, which means you have more to memorize. And there's also the concept of a borrow, which we'll deal with later. So now we want to kind of think about those concepts that we know, which is carry. So once again, the concept of a carry means if I add 2 digits, okay, the resulting value can be more than what a particular digit can represent. In that case, we have the concept of a carry, which is basically saying, well, me as a single digit cannot represent this particular value. So you over there, the more significant digit, I need you to take care of this portion of the value that I need to represent, because I cannot represent the entire thing. Okay? Is that okay? In a base 10 number, what is the range of values that each digit can represent? Can anyone tell me from where to where?
0 to 9.
From 0 to 9. Very good. What about base 7? From 0 to 6. What about base 2? 0 and 1 only. Whoa, we don't have a whole lot of bases, do we? Okay, so now let's talk about the multiplication table of binary. I'm thinking about whether to use this or to use a mouse pad. Let's just use this. Okay. So 1 plus 1, and I will say in base 2. What do you think it is? So you instinctively know the value of the addition is 2. This is the quantity. But the question is, how do you represent this quantity in base 2? What is the problem? The problem is in base 2, a digit can only represent a 0 or 1. So let's say I am one digit. I'm this particular digit here. My job is to represent how many ones there are in the number. But guess what? I cannot represent this value anymore. So what do you think should happen? There's a carry of 1. Okay? Because I cannot represent the value, so I have a carry of 1 when I just represent a value of 0. So in base 2, this is the trickiest portion of base 2 addition, is 1 plus 1 is not 2, because a single digit cannot represent the quantity of 2. It will give you a 0 for this particular digit, but it will give you a carry of 1, because guess what? The next digit, what is the quantity, what is the power of 2 the next digit is representing? How many 2's we have? So that guy can deal with it. Is that okay? Yep.
So if there was a third row of an addition, the 1 would just come down and then another 1 would carry?
Well, we'll carry out multi-digit addition later on. But for now, we just have to remember 1 plus 1 is a 0 and a carry of 1. Okay? What about the other, cases? Well, the other cases turns out to be pretty easy in base 2 or in any base. 0 plus 1 in base 2 is just like in any other base. It's just 1. 1 plus 0 in base 2 is just 1, just like in any other base. And then we have 0 plus 0. It's just like in any other base. It is just 0. Is that okay? So these three cases are pretty trivial. Okay? The only case that is kind of tricky is 1 plus 1 in base 2 is not 2. It is a 0 with a carry of 1. The other way to be more complete, with the other three trivial cases, we'll even say that there's a carry, but the carry is 0. So this has a carry of 0, a carry of 0, and a carry of 0. Do we have any questions about the 4 cases of single-digit addition in base 2? No? Okay. Don't you think elementary school, students would really appreciate base 2 now? There's not much to remember. I mean, these three they are kind of intuitive. This is the only one that is kind of tricky. But it is no more tricky to someone who is new to addition than 5 plus 7 is a 2 with a carry. It's the same concept. It is tricky to all of us because we have been poisoned by base 10. Now we have to detox first and then relearn something that's actually easier. Yep. What do we do with the carry? Well, we just have to remember there is a carry for now. Okay? All right, so based on this, we can now make a table. So we make a table, it's kind of a truth table. We have x, we have y, which are the independent variables. And then what we do is we'll have c, let's say r to represent the result, and then c to represent the carry. The result is the digit that is here. That's the result of that column. The carry is to indicate whether we have a carry of 1 or a carry of 0. Is that okay? Does everybody understand what R is representing and what C is representing? Okay. So we'll make this little table, which is for the most part just copying stuff that is already on the upper portion of the whiteboard. 0 plus 0 has a result of 0 and also a carry of 0. Is that okay? 0 plus 1 has a result of 1, a carry of 0. 1 plus 0 has a result of 1 and a carry of 0. The only one that is a little bit tricky is the last one. 1 plus 1 has a result of 0 and a carry of 1. Are we doing okay so far with this? This is just a kind of tabular, format of what we have been talking about. Are we good? Okay. So what we want to do now is to say, well, but so far these concepts are arithmetic concepts, right? The concept of a carry, the concept that, the value of 2 is more than 1, which is the largest value a single digit in base 2 can represent. It's comparison. We have to understand this is more than the other one. They are arithmetic operations. Do we know how to do arithmetic operations using transistors? No. What do we know about using transistors? We know how to do all the logical operators, don't we? We start with NAND, and then we move on to NOT, then we move on to AND, then we move on to OR. So we can do all kinds of Boolean operators using transistors. But how do we compare numbers in transistors? We don't know. So the next thing we want to do is to say, is there a way to convert arithmetic concepts that we have just talked about into Boolean concepts that we already know how to implement? That is the next jump of concepts. Okay? So we'll do the easy one first. And let me see how much space do I have. I do have enough space. Okay, so we have x, y, and this time we only focus on c. Okay, this is just a copy of what we already have, but I just want to kind of focus on these three columns. 0, 0, 0, 0, 1, 0, 1, 0, also a 0, 1, 1, and a 1. Okay. Do you think this resembles some truth table that you might have encountered already? It is just regular, not NAND. This is just regular AND. Okay? False or false is false. False or true is false. True or false is false. True and true is true. So instead of looking at zeros and ones as values, if I reinterpret 0 as false and 1 as true, this can be done using conjunction. And nobody yay except for me. Yay! Why? Why is this important? Now we can do carry using just logical operators. Okay. Huh? Well, the other one is a little bit more tricky, so we'll talk about that one. So now we define the function carry, okay? The carry of x plus y is really just x and y. Woohoo! No arithmetic concept, needed. We just do it in Boolean operator. Excellent. I like that. Yep. Huh? Which function? Oh, this one? Yes, it only works in base 2. Only when base 2 digits this will work. You're correct. Okay, so if this one is kind of cool, let's look at the result, the R column. Okay, I'm going to open a new slide here. So once again, this is just a copy of what we already have, except we are focusing on R this time. 0 plus 0 has a result of 0. 0 plus 1 has a result of 1. 1 plus 0 has a result of 1. 1 plus 1 has a result of 0. Darn it. We don't have a single, well, actually we do, but we'll talk about that. But out of the operators that we talked about in this class, which is NAND, NOT, and OR, none of it is going to give us this R column. That's kind of not so nice. But let's see if we can use an expression so that it will give us the same value. Because remember, I don't really need a single Boolean operator to give us what we want. I can use an expression. I can use a Boolean expression to give us what we want and still accomplish the same thing. Because the bottom line is to implement an arithmetic concept, but only using transistors. Yes?
Logic operator for that. The exclusive OR.
Yep, exclusive OR would do it. Yep. So you're correct. So we can use exclusive OR, but since we have not talked about exclusive OR yet, we'll do it the long way. Okay. So I'm going to propose this. Rxy, which is the result of adding x and y, x, y both being a single binary digit. And using C syntax is just going to be x and not y, or not x and y. Okay. Do you think this is going to do it? Maybe, maybe not. But how do we know? How do we check that this expression is really going to give us exactly the same column as R? You can use a truth table. Exactly. Okay, so let's do it kind of informally. Let's say x and y are both false. Okay? False and true is false. True and false is false. So false or false is false. That's match. Okay. Next one. One is true, one is false, and one is true. Okay. X is false. Actually, if X is false, I don't even need to bother with the red, right? So this whole thing is false. Not X is true, but Y is also true. So we have true and true. This whole thing is false. This whole thing is true. So now we end up with false or true, which is true, right? The next row is kind of the mirror image of the previous one. So they end up with exactly the same result, which is a 1. So we only have one last row to deal with. If X is true and Y is true as well. Well, if X is true, then this is true. But since Y is also true, not Y is false. True and false is false. X is true, not X is false. I don't need to evaluate the rest of the conjunction because the whole thing is going to be false. So now we end up with false or false, which is false. Matches exactly. So now we know at least a kind of long and clumsy way, but it is Boolean. Okay, it only involves Boolean operators because and, or, not, they're all Boolean operators. Now, if you want to, we can actually build a circuit made out of only P and N transistors to do this, right? Because we know how to do it. We know how to implement a NOT using NAND. We know how to implement an AND out of NAND. We know how to implement an OR out of NAND, right? And we know how to make a NAND out of 4 transistors. So that means, in theory, this whole thing can be done with a big mess of P and N transistors. Am I going to ask you to do that? No. Because that's just busy work. I don't like to do busy work, and I don't think you should do busy work either. Okay? But in theory, it can be done, right? And that is the significant part. The significance of all of this discussion is an arithmetic concept can now be done using transistors. We can build a circuit to do this. Are we good? Are we doing okay so far with this? Yes? Okay. But so far, the tools that we have talked about, which is the result of adding 2 bits and the carry of adding 2 bits, they're really only good for adding single digits. So the next question is, well, how do we deal with multi-digit addition then? Is that okay? So what we do now is we look at a multi-digit addition, but in base 10. Because I want to make sure that you guys can start with base 10 and then transition to base 2. Because the concepts are exactly the same. Except one we are used to, and the other one is kind of new to us. So I will just kind of present 726 plus 100 and let's make it fun here. 175. I'm hoping you guys know how to do this. Yes? Okay. But the way I'm going to do this is a little bit weird. Okay? So the way I'm going to do this is weird in the sense that I'm going to do it kind of using just the R and the C, but in base 10. So I look at 6 plus 5. The result is a 1. And it has a carry of 1 here. I look at 2 plus 7. The result is a 9 with a carry of 0 so far. Okay? I look at 7 plus 1. The result is an 8. And the implicit carry to begin with is a 0. Is that okay? I know this is not how you write out a long addition, but I'm doing it this way because I'm showing you that there are actually 2 additions involved when you think there's only 1. Okay? So once again, let me explain this one more time. 6 plus 5 is 1 with a carry of 1. 2 plus 7 is a 9 with a carry of 0 so far. 7 plus 1 is 8 with no carry so far. Okay? So this is one addition. I only make use of the result and the carry. Is that okay? Then I apply addition again. So now I say, what if we add up these two rows? So now we end up with 1 plus 0, which is a 1. 9 plus 1, which is a 0, but with a carry of 1. So we cross out that 0 and turn it into a 1 now. And then we have 8 plus 1, which is a 9, and there's no overall carry. Is that okay? Does everybody understand what I have just done? I know it is not the way you normally write out a multi-digit addition, but that's only because I make the carry having its own role. Are we good? Yes? So are we ready to abstract this? Because computer science, programming in general, is all about abstraction. I give you a few concrete cases, you work it out, and then we try to abstract it and say, in general, how does it work? Okay, so we're going to abstract this. So how do we abstract something like that? Well, instead of using actual digits, this is what I'm going to do. x2, x1, x0. So x0, x1, x2 are representing the 3 digits of the first number that we are adding. Okay? And you might probably know that already. We're going to have y0, y1, y2 to represent the 3 digits of the second number that we are adding. Is that okay? So the next row, I'm going to label, okay? These are just labels for the digits, so we can talk about each digit later on. So the next row, I'm going to label this Q0, Q1, and Q2. And I'll label this as K0, K1, and K2. And then the final result is going to be S0 for sum, S1, and S2. Okay? So instead of giving you concrete digits to work with, now I abstract everything and say, well, I'm going to give you x0, x1, x2, y0, y1, y2 as the input into this whole thing. Our ultimate objective is to figure out what is s0, s1, s2, but intermediate, the intermediate digits, which are q0, q1, q2, k0, k1, k2, we kind of have to figure out a way to do all that stuff too. So does everybody understand why we are converting from concrete digits into something that's kind of awkward, right? Because every digit is now replaced by a variable. All right, so given this is the representation, can someone tell me how we figure out each Q? Well, we'll figure out Q0 first, and then try to generalize from that. Q0 is, sorry? It's the result, right, of adding x0 and y0. So it's r in parentheses x0, y0. Okay, very good. So it really is just r, x0, y0. Okay, that doesn't seem too bad. But in general, it's true for all of the q's. So qi is the result of adding xi and yi. Is that okay? Are we good? Okay. That doesn't seem too bad. K0 is assumed 0. Okay, so we'll just write it here. K0 is assumed 0. But K1 is a little bit tricky, don't you think? Because K1, who can contribute to a non-zero K1, which is this guy here? There are 2 sources, aren't there? Because one source is these 2 added together. The second one would be these 2 added together. Now, for column 1, it is not as big of an issue because we know K0 is going to be a 0. So it cannot be coming from that. But in general, we do have 2 sources to generate that particular carry. So if we look at K1, then you can say, yeah, K1 is easy because K1 can only be coming from C, the carry, of adding x0 and y0. But when you look at K2, it's not that simple anymore. Because when you look at K2, sure, it can come from x1 plus y1, but it can also be coming from, let's see, q1 plus k1. Is that making any sense? If you think about this particular carry, there are two sources to make it a non-zero. It can be these two digits contributing to this carry, but it can also be these two digits contributing to this carry. Now, can they both contribute at the same time? We'll kind of hold that question for a while. Okay, we'll answer that question later on. But they can both contribute. We know that one or the other at least can contribute. Is that okay? So generally speaking, we can now say that ki plus 1, k of I plus 1, oops, there we go, is the carry of xi, yi, plus the carry of qi, ki. Just in general. Are we good so far? Okay. So I know there's a lot of symbols on the screen, and I'm turning something that's really simple into something that has a lot of symbols. But that's for a reason, okay? Because once we understand the mechanism of doing this in general, then we can reapply this in base 2, and we'll find that, oh, we can actually do everything in transistors in base 2. Okay, but we are not quite done yet, okay? Because now we know how to figure out the Q and the K's. The X and the Y's are easy. They're inputs, okay? They're just given to you. Here, start with this. But the Q's, well, we kind of have to do some computation to get to the Q's. The K's, yeah, we have to do some computations to get to the K's. But now the question is, how do we get to what we really want, which are the sum bits, the S? How do we get to the S? Well, let's figure out. What do you think is sum 1? Okay, S1. Okay, S1 is this guy here, which was this guy over here. How do we get the 0 in the concrete example? Yeah, it's just the result of adding the 9 and the 1, right? So how do we express it using the notations that we have already discussed? It's the result of Q1, K1, okay? And in general, Si, which is the ith bit, now remember this ith bit starts with 0, okay? In general, it is really just the result of adding Qi and Ki. Are we okay? All right. So let me just kind of highlight the ones that are important, the ones that are totally abstracted and they are really important. This one is important. This is the actual answer that we want. This one is kind of important because it tells us all the carries. And this one is important even though it's kind of simplified. But these three are the ones that are really useful because they tell us how each digit relates to other digits in a multi-digit addition. Yes?
What about the base case for K1?
Um,
Because it's not, is it technically?
it is not really important. You mean this one here? It is not really important because sometimes we do not actually make an assumption. So we kind of want to be careful of whether we want to assume K0 is 0 or not. In a normal calculation, yes, it is. Calculations that we do not want to make that assumption. So are we good so far with this? Okay. So with this, we can now actually expand out the equations and say, okay, so what is SI? Well, it is the result of this, blah, you can expand the equations. Because do you think the relationship between the digits using R and C will change whether it is base 10 or base 2 or base 7 or base 3? Do you think that these equations will change? It does not change, because this is how we carry out multi-digit addition regardless of the base. So that means the only thing that's going to change is in base 2, our R function can be done using Boolean operators. Our C function can also be done using Boolean functions. That's the only thing that changes. In base 10, we cannot. Okay, in base 10, the R function cannot be done using Boolean operations, because 5 plus 7, 5, 7 would give you an R of 2. 5, 7 would give you a C of 1 in base 10. Okay, so it cannot be easily done using just logic gates. But in base 2, it's pretty easy. We talked about how to convert those into logic gates. Today is Thursday, so I do want to give you some reading assignment to do over the long weekend. Well, not long weekend, but it is a weekend. So we do have some time between now and the next class. So you definitely want to go through all the material that we have already gone through. So section 4 is kind of what we are at this point. It's basically only about the notations. And then section 5 is starting to focus on just binary numbers. Okay, and you should finish the entire thing, the entire module, at least finish reading it at least once by next Tuesday, because this is what we'll be talking about on next Tuesday. Now, let me just kind of point out, that there will be something that's a little bit. Section 6 does not seem to be important, because all it says is, but wait, there's more. Well, what I did not write is, but wait, there's way more. Because you have to read it carefully. There's a certain derivation here. Okay, so do not be intimidated by this. I will explain it. Okay, in this class, you are not required to prove something like this. Okay, I present the proof into this material because I need to convince myself that it is correct. Okay, so it is note to self. On the other hand, I will go over this because I think an exposure to Boolean algebra would not hurt. Okay, so I will go over this. You can glance over it. If you can understand it, great. If you cannot understand, the entirety of it, it's okay. We'll talk about it on Tuesday. And then later on, it will have expansions like this and something that looks like this. So once again, if you do not understand what the big wedge or the big V means, it's okay. We'll talk about that. But try to finish reading the entire module and jot down any questions that you might have. Then on next Tuesday, we'll go through the rest of the module. And if I do not address your questions, or if I do not sufficiently explain something that looks really mysterious in the notes, let me know. Then we will talk about it in class. So right now we're going to transition to the lab. The lab activity should open at 10:30 automatically. And I cannot remember the passcode, so I'll talk about the passcode in the lab.